Alright, so we're going to be talking about something that's important for the pseudo-inverse, and that is, what is the rank of the matrix? Okay, now, theoretically, there is no issue here. Theoretically, rank equals the dimension of the column space of A. And so uh, we just find the column space of A for the basis for it, and that's it. However, if you have a very large matrix and you plot the singular values, so this is like the number of the singular value down here. So this is like the first one. I guess that would be the first one, and we won't plot that one. 2, 3, 4, 5, and you plot all of your singular values here. Often what you're going to see is that the singular values just drop off like this. They don't increase, right? They're strictly decreasing because we're ordering them that way, right, in the matrix S. Sigma 1. And so this is a plot of all your sigmas. Sigma K, I guess. Well, down to sigma N. Yeah. And so the question then, if you have a curve like that, is what in the world would be the rank? And so hopefully it's not so hard to determine from like that. So instead, what you're really looking for, or what you're hoping for, is that you'll see that there's a big break or a jump, right? So um, this might be like index 10 and this would be 11, and so in between 10 and 11 you'd see this big break here, and so in this case right there you would say that the rank is 10. Okay, so that's kind of the easy case. Hopefully you see something like that. Okay, so what do you do if you run into something like this first case? Well, there is something we can do, and that is one will, instead of looking at the singular values, we'll go ahead and square those so that you're looking at the eigenvalues. So just as a reminder, right, those are the singular values squared. Okay, and the reason we're working with the eigenvalues is that as it turns out, the eigenvalues are closely related to statistical variance in the data. Let me see if I can spell that. Okay. Statistical variance in the data. Okay, it's getting late. All right, so we're going to work with the lambdas instead. And so what people will typically do is they will normalize the lambdas. And so let's say that lambda I tilde is equal to lambda I divided by the sum. Let's say j equals 1 to n of all the lambdas. So this is the sum of all the lambdas. Right? And so the lambda i's, the normalized values will be between 0 and 1, right? And so they're almost like probabilities. They sum to 1, and they're each between 0 and 1. Okay, and so what people will do is they will say, let the rank be the number where the sum of lambda 1 tilde plus lambda 2 tilde plus lambda k tilde is greater than or equal to some cutoff, say 0.99. So it's the first value where this happens. And so you would say um, the k minus first is less than the cutoff. Okay, 99% is a pretty good, generic value to use. Um, there is some newer work from 2014 that's kind of interesting. I haven't had a chance to read the paper deeply, but um, there are two statisticians that have a nice optimal hard threshold for singular values. Um, and so that's some newer work that might be of interest. Okay, but for us, we're just going to either take one of these two cases. Um, I should say that in the built-in commands, built-in commands for rank typically use some cutoff value. They'll usually call it a tolerance, TOL for tolerance, and it's usually something like machine epsilon, whatever that is. It's about 10 to the minus 16th in MATLAB times m or n, depending on which number is bigger, and they'll use that as their tolerance level. In other words, that's the level at which any number below that is just considered to be zero. Okay, so it's interesting to read about how these programs actually compute the rank. So you might take a look. In MATLAB, it would be help, space, and then rank. I'm not sure what it is in Python. I usually just Google it. So you can Google it. Help rank in Python, or rank in Python. Okay, I've gone on and on long enough. Okay, I think I will let you read through the programming examples on the next page. That's page 58 of these notes, the notes that were out today. Because remember, the page numbers change from day to day since I'm including code into the stuff. So I'll put the homework on the class website, but basically you're just going to work through a couple of problems on pages 59 and 60, and then you might start with those first, and then watch the video about the clown in the SVD, and then try out the second part. So all of the homework questions are going to be typed up on a computer lab sheet for today. All right. Have a good weekend. I'll see you later.